Combustion analysis is a way of finding an empirical formula for certain specific types of molecules. And what the type of molecule is that's good for is hydrocarbons. So it's for finding the formula for a hydrocarbon. And a hydrocarbon is something with hydrogen and carbon in it. And it may also have another substance in it, some other atom. All right, so when you do a combustion analysis, you assume a complete reaction. In other words, until at least one of the reactants runs out. Okay, so the general formula for hydrocarbon combustion is you have some compound with carbon, and I'm going to use M as a subscript because we don't know what the subscript is, N as a subscript for hydrogen because we don't know what it is, and we'll do one with oxygen and use the subscript P. So we don't know what M, N, or P are. We don't know the formula. All right, then we react it with oxygen, and it forms carbon dioxide and water. So that is a hydrocarbon combustion reaction. And you use the amounts of carbon dioxide and water to find the amounts of carbon and hydrogen in the substance. If you notice that you'll produce one molecule of CO2 for every molecule of this, however, by how many, what M is. Okay, so if M is 2, you'll produce 2 over here. If M is 3, you'll produce 3 over here. Okay, and then with water, you get 2 hydrogens in every water, so N divided by 2 will be the number of waters you produce. Okay, so you're going to find the empirical formula of the hydrocarbon, CmHnOp, from the mass of CO2 and water produced. Okay, so I will do an example in detail and then have you do an example. All right, so the one we're going to do is, we'll say a molecule containing only carbon, hydrogen, and oxygen is completely combusted. 100 gram sample is used and it produced 146.6 grams of carbon dioxide and 60.4 grams of water. Okay, so we'll use those numbers and this number, the original amount, to find out the formula of this hydrocarbon. All right, and I've outlined the steps already, and we're going to then fill in for this example what we do. So first we need to find, from the grams of carbon dioxide and water, we need to find the moles. All right, so you know how to do that. Take the amount of carbon dioxide and turn it into moles by using its molar mass, 44.01 grams per mole. So we get 3.331 moles of CO2. All right, same for water. We had 60.4 grams of water. Use its molar mass, 18.02 grams, and that gives us 3.352 moles of water. All right, so that's moles of carbon dioxide and water. Now, step 2, we convert those numbers to moles of carbon and hydrogen, which is fairly trivial. Every mole of carbon dioxide has 1 mole of carbon. So since there's 1 C in CO2, that means we have 3.331 moles of carbon. Okay, but there's 2 hydrogens in water. So we have 3.352 times 2, which is 6.704 moles of hydrogen atom from the water. Okay, then we're going to convert that to grams of carbon atom and hydrogen atom so that we can add up how much of that 100 grams total we started with is due to carbon and hydrogen. The remainder will be due to oxygen. Okay, so we're going to convert these. Start with carbon, 3.331 moles of carbon, and use the molar mass of carbon, 12.01 grams per mole, to get 40.01 grams of carbon. All right, hydrogen, 6.704 moles of hydrogen atom times 1.008 grams per mole for hydrogen atom. And that gives us 6.758 grams of hydrogen. All right, so we add those two up, which will be about 47, and subtract it from the total mass of the substance we started with. Okay, the total was 100 grams compound of unknown formula. We subtract off the 40.01 grams of carbon, we subtract off the 6.758 grams of hydrogen, and that gives us 53.24 grams of oxygen. All right, so we already know the moles of hydrogen and carbon. So we could do, if it was just hydrogen and carbon, we could have done the empirical formula way back here. But we needed to know how many moles of oxygen. Now we have grams of oxygen, so we can produce number of moles. And so we take our number from here, 53.24 grams of oxygen, and convert it into moles using molar mass. And that gives us 3.33 moles of oxygen. All right, so now that we know the moles of oxygen here, and we know the moles of hydrogen here, and we know the moles of carbon here, we can use those three numbers in ratios. And you can probably tell the ratio right now. We have 6.5 divided by 3 1/3, about 6 2/3 divided by 3 1/3, and another 3 1/3. Okay, so you may be able to figure that out already in your head, but let's do it officially. 6.704 moles of hydrogen, and we have pretty much the same amount of both carbon and oxygen. So I'll do it for carbon, but it's the same for oxygen. It gives us approximately 2. Okay, so there's 2 hydrogens for every carbon, there's 2 hydrogens for every oxygen, which tells us the empirical formula is H2CO. And again, the molecular formula could be any multiple of that. All right, let's have you try one. Vitamin C, likewise, contains carbon, hydrogen, and oxygen. We're going to start with 1 gram of vitamin C. So you're going to try to figure out the formula, the empirical formula for vitamin C. It underwent combustion. We made 1.5 grams of CO2 and 0.41 grams of water. All right, so stop the video and work on it yourself, and I will proceed to do it. All right, step 1 was finding moles of carbon dioxide and water. So we'll convert these numbers. Just like we did before. And you should get 0.034 moles of CO2. For water, 0.41 grams of water. And we get 0.023 moles of water. All right, so step 2 is convert those to moles of carbon and hydrogen. And for carbon, it's exactly the same. Moles of C equals moles of CO2 equals 0.034 moles of C. All right, moles of H, hydrogen, equals 2 times the moles of H2O. So it equals 0.023 times 2, or 0.046 moles of H. And again, if we only had carbon and hydrogen in our formula, we'd be done. We'd have to take ratios, but we'd be almost done. But we also have oxygen, so we have to figure out what that is. So we got to convert these numbers back to grams of elements. 0.034 moles of carbon times 12.01 grams per mole gives you 0.408 grams of carbon. 0.046 moles of hydrogen gives you for hydrogen gives you 0.046. No, wrong. Yes, it does. Still the same thing. Okay. 0.046 grams of hydrogen. All right, and we can total those up now, or we can subtract them one at a time. I'll total them now. The total of carbon and hydrogen is 0.45. Remember, we had 1 gram total of substance. So we take the 1 gram total and subtract off 0.454 grams of carbon and hydrogen, and that'll give you the number of grams of oxygen. And then we convert that back to moles of oxygen. 0.546 grams of oxygen times 1 mole for 16 grams of oxygen gives us 0.034 moles of oxygen. So now we have our third number for the formula. We have 2 up here, we have the third one. Take mole ratios. So if we use the largest one, that's step 6, moles of hydrogen over moles of carbon or oxygen, which are about the same, we end up getting 1.3, which is not that close to an integer. So we'll use trial and error to come up with integers. If you multiply this by 3, you'll get a whole number, pretty close to a whole number. And so you multiply it times 3, and you get the smallest whole number ratios would be C3O3H4. You'll find that it's a ratio of 3 to 3 to 4. This one times 3. We'll give you that ratio. Okay. Finally, I have a problem that is not combustion related, but is combines a couple of different concepts from this chapter in one problem, so I thought I'd go over this now. This reaction is with zinc and copper sulfate to produce zinc sulfate and copper, and I have an amount of zinc. Well, you should read the problem. When 60 grams of zinc are allowed to react with 120 grams of copper sulfate, 43 grams of copper are obtained. So let's put these numbers under here. We have 60 grams of this, we have 120 grams of this, and it produces 43 grams of copper. And the question is, what are the limiting reagent, the theoretical yield, and the percent yield? So this is a problem that combines limiting reagents and yields in one problem. I would suggest you stop this video and work hard on this before you go on. Because if you just watch me do it, you aren't going to learn nearly as much. Okay, so what do we have to do? First we have to figure out what's the limiting reagent, reactant, by seeing how much copper each of these would produce. Alright, so we'll start with the zinc. 60 grams of zinc. Convert it to moles using 65.4. Whoops. I'll do that again. One mole zinc, 65.41 grams per mole. And it's a 1-to-1 ratio from copper to the zinc, so we'll do 1 1 1-to-1 mole ratio, and then we'll convert it to grams of copper. 63.546 grams of copper per mole. So if zinc were the limiting reagent, we'd get 58 grams. Whoops. 58 grams of copper. All right, let's do it with the copper sulfate, assuming it's limiting. 120 grams of copper sulfate. Convert that to moles with the molar mass of copper sulfate. And the mole ratio there is also 1-to-1. And then we use, again, the mass of copper to get grams of copper. And this gave us 48 grams of copper. So the limiting one is this one. It's smaller, which means the copper sulfate is our limiting reactant. Okay, so we now know that the answer is either B or C. So the question is then, how much do we actually make? And we said 48 grams, which tells us it's answer B. Let's go on and calculate the yield. Okay, so what we calculate, the amount we calculate you could make, is the theoretical yield. The percent yield, even though there's no more choices, I will practice that. We got 43 grams actual over the amount that was, so there's the amount that was actually made over 48 theoretical that we calculate. And then we multiply all that by 100%, and that gives us 90% yield, just like answer B said.